Hello, Internet. Today I want to talk to you about TensorFlow code, how to program Word2vec. You know, this is the very famous methodology to do some word embedding that is not content sensitive. So this means if you have a word like bank, you can have the bank right next to the river where you can sit down, or you have the bank in the middle of the city where you deposit your money. Word2vec and TensorFlow. I will use the official tutorial by TensorFlow, apply TensorFlow 2.7 here in my COLAB notebook, in my Jupyter notebook, so you can run along and see the code that we are using. It is the official notebook. I just put some additional thoughts into it, and here we go. Now, if you are familiar with Word2vec, and I guess you are, because it came up in 2013, just a very short summary. We have here Word2vec is based on two principles, skipgram and negative sampling. Negative sampling is, of course, the interesting part of this, but let's start with the training objective for the skipgram model, which is to maximize the probability of predicting the right context word given a target word. So if you have a target word somewhere in the middle of a sentence and you remember BERT, where you have the masking going on, this is a context-sensitive model, we have now to predict the word before and after the target words. And we call these words context words. And for a sequence of words, word 1, word 2, word 3, we have now an average logarithmic probability that we can write here in this notation. And of course, if you see here our logarithmic probability, the probability itself is a basic skipgram formulation where we can use the softmax functions. Of course, you know that computing softmax is quite time-consuming, so people came up with the noise contrastive estimation loss function, which is an effective approximation for your softmax. But you can simplify it even further, and your NCE loss can be simplified to negative sampling. A negative sampling is beautiful because it brings down all the problematic softmax calculation to a classification problem between a context word and a number of negative samples. So very easy, you have a pair of words and you have a Boolean logic true, or you have Boolean value false. So you just have a classification problem. So let's start with it. But before, for all those of you who were interested in the original literature, of course, you know, 2013, Google, Thomas Mikolov, and he wrote this very famous paper where he went into the theoretical approach of the skipgram model, where we have here, as I showed you, the probability between a word 1 and a word and the close proximity, given a sentence of words. And he then tells us, okay, this probability you can use the softmax function for. So this is the famous thing here. You put in for the probability p, you put in here this exponential function, and you have your softmax. Of course, he already noted that it is computationally efficient to approximate the full softmax with a hierarchical softmax, and not going into the detail. He also mentioned that an alternative is noise contrastive estimation, NCE. And of course, you would not believe it. You can also simplify this even further as what it is called a negative sampling, NEG. And he writes, and this is one of the insights that he found, when he compared those three methodologies and those three simplifications, he shows that the negative sampling, the easiest simplification, outperforms the hierarchical softmax and has even slightly better performance than NCE, the noise contrastive estimation. Therefore, we came up with very easily a negative sampling approach. And now our job is to put negative sampling into TensorFlow 2.7 code. If you're interested in negative sampling, there's a beautiful paper here. I'll leave you the link also in the description of this video, where they tell you negative sampling is simply a simplified variant of NCE, where you neglect to subcontract off your logarithmic function for training. And it is noteworthy that in negative sampling, we are optimizing a function to approximate something that depends on the sampling distribution. And this will make the result highly dependent on the choice of your sampling distribution. This is interesting. Keep in mind the sampling distribution. Already Mikolov mentioned this. So here we go with the code. The first, of course, here is we switch over to our Jupyter lab and we can run the code in real time. So what we do is we have our NumPy, we have our TensorFlow, we have TensorFlow Keras, and we have, of course, our tf.data for the data pipeline, our autotune function enabled. And then we define, just for demonstration purposes, a sentence. And this sentence, as you can see here, has 20 words. And we say, okay, here we go. What are our tokens? Our tokens are, of course, our words. This is the most simple approach. And you know that there are quite a lot of tokenization methodologies, but let's stay simple because we want to just get a feeling for Word2vec in TensorFlow. And we are using not the gensim approximation in Python and in CPython, because I want to show you how you can do this yourself in TensorFlow. So here we go. You can create your vocabulary. You can create your inverse vocabulary. This is self-explaining more or less. You have here the numerical index for all of your words. We have 20 words and we have a padding in front of, so this is value 0. And then you say, okay. If you want to have the size of your vocabulary, you have 22 because you have a special padding. Then we start with generating skipgram for this one sentence. And we have here on the left side the verbal explanation. As you can see here, the same headings, generate skipgram for one sentence. And here, more or less, here in our Jupyter notebook, we have also a little bit of text, but primarily we can experiment with the code. And what we do, we have a beautiful function, and this is called TensorFlow Keras Pre-Processing Sequence Skipgrams. And what it does, this function generates skipgram pairs of words for us. We just have to give it a word size. Let's say if I have a target word, I want to have the 2 words to the left and the 2 words to the right of this target word. So I will have 4 specific words in this vicinity, in this interval, and I will call them, just hold on a sec, context words, of course. So we use the TensorFlow function to generate our skipgrams. As you can see here, we deactivate our negative samples because for the negative samples, we hear in the official TensorFlow tutorial, they tell you, hey, wait, we do something special. So negative sampling for skipgram. Just let me execute this here on the right-hand side to show you the positive skipgrams that you will get, that you have an idea what is the output. So you have here your target, indicate your target index, the numerical value of this word. The word is 11. And you have the value 12, because remember, we have a padding right in front of. And of course, you have the numerical value 10, the integer 10, and this indicates, this encodes your word 9. Whatever you have, I just put some alphanumeric code right next to word, so you see how the flow goes on. Negative sampling. Negative sampling is really interesting, and we have here a predefined function that the official TensorFlow tutorial uses. tf random log uniform candidate sampler. And this is a function to sample a number of negative samples for a given target word in a window. you can call it, and you have for the number of negative samples, you have 5 to 20 for small data sets and 2 to 5 for large data sets. It's an empirical value. Look at the code here on the left side. You have your positive skipgram 0. So the first one, and this is here, if I follow here the official publication, the first one is, where is it? Here. The first one from our positive skipgrams is 2 and 4, and indicating the words white and shimmered. White is our target word, 2, the numerical value 2, and shimmered is our context word, and this is a word pair. And of course, the numerical value for shimmered is 4. So remember 2 and 4. And now what it does, it tells you, okay, we take 2 and 4, we set the number of negative samples, this is 4, and then we apply this random log uniform candidate sampler. And this sampler is interesting because what you will find out here, the sampler itself has no idea about the target word. What it does is, if we go there, where's our sampler? Here is our API. Sampler simply states samples a set of classes using a log uniform base distribution. The operation randomly samples a tensor of sampled classes from a range of integers. Now, the range of integers is, of course, the size of our vocabulary, the amount of words we have in our text. And it just picks samples. And they have to have a distribution that should be log uniform or Zipf distribution. And this sample is useful when the target classes approximately follow such a distribution if they represent words in a lexicon sorted in decreasing order of frequency. So the frequency of use of a word in decreasing order, then apply this sampler. If your classes are not ordered by decreasing frequency, do not use this operation. And now you will understand, if we apply this huge TensorFlow code to our example here, you will find that as a result of negative samples, and remember our positive skipgram was 2 and 4, we suddenly get also a 4. And remember 2 and 4, 2 for the target word and 4 for the context word, is positive. And suddenly we have here a 4 as negative. So how could that be? Well, we do not have a uniform distribution. We do not have we have just one sentence with 8 words here. So it does not work out. It gives us a result that is simply wrong, because 2, 4 cannot be right and wrong at the same time. And you see this if you go on and you construct now your 3 data sets that you need for your data input pipeline. What you get here is the 2, this is our target word, 2, and then the context word, 4. And we have now a boolean or a label, 0 or 1, and 1 is true. So you have for 2 and 4, this is a true combination of words, of word pairs. But for the combination 2 and 1, this is a false one. But then look, 2 and 4, so identical value 4, like here 4, and you tell now the system to learn that it is false, although you tell him, hey, here I tell you that it's true. So this example does not work. It cannot be true and false at the same time. So this is not working. What I did, I have this here now, and we switch now again to the right side. Let me just magnify it a little bit. Come on. That's why I have here 20 words. And I hope that with a little bit higher amount of words, maybe we can smoothen the curve out and come close to it. So let's have a look at this. We have here again our positive skipgram 0, where I have the target word encoded in the numerical value 12, and my context word in 10. Exactly, I have a window size of, my window size is, just hold on, 2. So 10 and 12, perfect. This is just the maximum window size. And then I have my context class of 10 because this is my context word, the numerical encoding of my context word. And then I look at the negative candidates. And those are my 1, 2, 3, 4, 5. I have chosen 5 here. The set of number of negative samples per positive context. I've chosen to have 5 negative pairs here. And as you can see here, 12 and 10, you would not expect to have 11 in between, because of course, from the target word 12, if you go just one word to the left, you will have the word encoded with 11, and this will be a positive pair. And this here, the system says it's a negative sample candidate. But of course, as I told you, our TF random something uniform candidate sampler has no idea about the positive pairs. So it just takes a class, and this is our vocabulary size, and it just samples randomly given a probability distribution that is not here. Because I have one sentence and just 20 words, and this function does not have any indication what is the positive skipgram that it should not label as a negative sample at the same time. Because if it's positive and negative at the same time, how should the Word2vec model learn what is the right one? So again, we see here, if we have 5 works, 2 works, 3 works, 7 works, but 11 is clearly in the interval between 10 to 12. So this should, in my opinion, be not a negative sampling candidate because it is a true positive skipgram. With this minor problem in mind, okay, again, maybe I do not get it, or maybe some mistake happened. I do not want to go into the code and just evaluate here the random log uniform candidate sampler from TensorFlow. As you can see, version 2.7.0. And now we construct our example. Let's go on like nothing happened. And let's see, how does our data input look like? What have we achieved preparing our input data for our Word2vec model? And here we go. This is it. Yeah, if I activate it, we can see it. This is the result. This is exactly what we want. We have here the target word. The target word is, let's make it a little bit bigger. The target word has the encoding 12, and our context words within the window of 2 is 10. So these words are close together in our window, and it gets the Boolean value of 1. It means true. This is a true combination that's really happening. And then we have our 5 negative examples to learn where we tell you, hey, this is not happening. And again, 5 is not happening, 2 is not within this window, but 11 is. 11 is definitely a word per 12, 11 is definitely a positive pair. 3 and 7 again, no. So there is a slight inconsistency even if we increase it. Maybe there's something I don't get whatsoever. And here we go, yeah. What else can we do? The sample size, no. Yeah, what is nice now is you can put all of this here in one definition. And this is exactly what happens here in our original TensorFlow tutorial. You say, define my function, generate the training data, dependence on the sequences, my sentences, the window size I define around my target word, the number of negative connotated word pairs, my vocabulary size, and then just some number for reproducibility. So what we do, we start as we always start. We set everything to 0. This is our 3 data we are looking to generate. We have our sampling table. Then we have our skipgram function from TensorFlow. And then we have our TF random log uniform candidate sampler, who is again here operating in all of its beauty. You know the problems associated with it. And then we just return the targets, the context, and the labels. And this is it. So if we define this function now, then we can go on and, for example, now download some text file. They have here in the official demonstration, they have Shakespeare. Well, okay, you load it and then you do some clearing, some lowercase, this punctuation, you clean up your text, you have a vectorization, you generate here your vocabulary again, as we have done before. You have your inverse vocabulary and you, vectorize the data in the text vector batch. Prefetch, you vectorize it, unbatch it, whatsoever. Yeah, let's run through it just to get an idea. These are the sentences we get. The vectorization. As you can see here, we say we have just a vocabulary size of 4096. Well, in reality, it will be bigger, but just for demonstration purposes. And our batch size, very simply, is just 1024. You know why. So we have here our words. These are ranked. We have here this high frequency word, the, and, to, of, you, my, and whatsoever. And then you just say, okay, just print my sequences. And we have 32,777 sentences, and our sentences look like, this is the first sentence, first citizen, and this is it, the rest is padded. Oops. And here we have now the numerical encoding. First becomes 89, citizen becomes 270, and so we go on. You know how this goes. And if we now run this generate training data on our data set that we have, Shakespeare data, you see that the calculation is quite fast because we just have a vocabulary size of 4K. And what we will end up with are our NumPy arrays, exactly what we need as an input data for our input data pipeline. And just to show you how it looks like, these are the arrays that you get, and they are in a very familiar form. You have here your target encoding, you have here your 1, 2, 3, 4 negative encoding, your context words encoding, and then you have here your labels. 1 is true and 0 are false. This is it. You see here that we have now a different size. We have, where is it? We have just 3. NS is 3, and we defined it here as our definition. Our negative sampling size is 3. This is the reason why we have here just 1 valued label and 3 label that tell you false. This is it for more or less. Now, the next step is just to define the input pipeline to optimize your TensorFlow dataset pipeline. You have here your from tensor slices, again, your targets, your context, and your labels. Then, of course, you shuffle around your dataset. You have a batch size, and then you do some caching. You want to have some in-memory calculation. And what is really nice, if you do a prefetch to further improve the performance, this is a real speed improvement if you have also your buffer size auto-tuned by the TensorFlow auto-tune functionality. And then you have your dataset, and this dataset is finally ready for the input to your Word2vec model. I will show you now, after almost half an hour just on data preparation for Word2vec, the model and the training of the model in the next video.